Hello AP Chem students and welcome to topic 4.9, oxidation reduction reactions, also called redox. The learning objective for today is 4.9.a, represent a balanced redox reaction equation using half reactions. So redox reactions, first of all, that stands for reduction and oxidation. So you know that all chemical equations need to be balanced before they can be used to analyze the outcome of a reaction. But redox reactions have a special balancing consideration because you have to think about the fact that the number of electrons that are transferred in the reaction must also be balanced. Now, we already talked about the fact that electrons are lost or gained during the process of a redox reaction, and we did that when we assigned oxidation numbers in topic 4.7. But in this this topic, we're going to talk about how you balance the equation to make sure that you have accounted for all of the electrons that are moving from one species to another. There is a process to do this from scratch, and you will see that out online if you go looking for balancing redox reactions. But in AP Chemistry, you only need to be able to balance a redox reaction if you're given the half reactions. And so half reactions are reactions that show either the reduction or the oxidation part of a redox reaction. And electrons are shown in these half reactions because you're separating out the two separate processes. Okay, so we're going to examine what that looks like. So this is what half reactions look like and then how they add up. So you can see here that we got iron 2 plus yields iron 3 plus electrons, and here we've got cerium 4 plus an electron yields cerium 3 plus. So then the question here is which is which, all right? So here we're going from 2 plus to 3 plus, so that is oxidation because you're losing an electron, which you can see because it's a product. Then this, of course, must be reduction, which makes sense because it's gaining an electron, which you can tell because it's a reactant. Now, if you look at the sum of the whole process overall, you would not see the electrons here because the electrons cancel out because they're found on both sides of the arrow. So just because they're not seen in the net ionic doesn't mean they're not there, right? So they are changing, they're transferring from one to the other. But this is how the half reactions can give you information about the electrons that the overall net ionic would not. So remember that oxidation, and this is what we just talked about, is a loss of electrons, which means the electrons will be found as a product in the half reaction, versus reduction, which is a gain of electrons. So your electrons will be found as a reactant in the half reaction for reduction. Tables of half reactions are almost always written as reductions. And so the half reaction that shows the oxidation has to be pulled from the table and then flipped before balancing the equation. So if you're just given a table of reductions, you should be aware that you can just invert it and then it becomes an oxidation. All the electrons that are lost during oxidation must be gained during reduction and vice versa, meaning that all electrons must cancel out. And so sometimes that means that you need to multiply a half reaction by a factor in order to make sure that all of your electrons cancel. So we're going to look at an example here. A student is studying the single replacement reaction that takes place between a strip of tin and copper nitrate. Write the net copper 2 nitrate. Write the net ionic equation for the process given the half reactions in the table below. So before I show you the actual answer here, I do want to point out that 3 of these half reactions use 2 electrons and 1 only uses 1 electron. So in the event that one of the half reactions that we use will be this one, we would need to multiply that half reaction by 2 so that it would show that 2 electrons are being transferred. Okay, so let's see if we're actually going to use it here. So a strip of SN means that it's SN solid. So that means that we're going to use this bottom reaction here because that's where your solid tin is. And we need to flip it because we're starting with solid tin. So there you go. And that's going to yield the SN2 plus the 2E minus. Then we've got our copper 2 nitrate. So that's copper 2 plus and 2 nitrates. Nitrate's part of the SNAP. So it's not going to be included. And so we're going to be looking for your copper 2 plus here. And that is this situation here. And you might remember from a single replacement reaction that we start with a solid and a solution, and we end up with another solution and then usually another solid. So then you can see that here because this copper 2 plus is being reduced to the solid copper. And so, right, we talked about the snap ion. Okay, so then we're going to use this equation as is. So then we're going to combine our half reactions, and this is what we get. So then the question becomes, do the electrons cancel out? And in this case, whoops, my red things are not in the right place because I scooted over my equation. Okay, let's try this again. And there we go. So my 2 electrons do cancel out. So I did not need to multiply these half reactions by a factor to have the electrons cancel out because each one of them was written with 2 electrons. So then this is our net ionic equation then. So when you see net ionics like this and you're looking at it and you're thinking, well, it's balanced just 1 to 1 to 1 to 1, but sometimes you see that there's coefficients there. Those coefficients are there to account for the electrons that are being transferred. So that is it. So what should you be able to do with this? You should be able to balance a redox reaction given a table of half reactions by considering both the conservation of atoms and the number of electrons that are transferred during the reaction. And that is it for Unit 4. And I'll see you soon for Unit 5, which is kinetics.